good morning. Today we will look into the details of the Boltzmann transport equation. So, yesterday we derived, derived in the sense that it is not a very rigorous derivation, but we showed that for a one particle distribution, so you basically convert the complex Liouville equation into the kind of solvable form of Boltzmann transport equation. So, this is a more practical equation to solve concerning the particle distribution compared to the more complex computationally expensive Liouville equation. However, you end up with having an additional term in the Boltzmann equation, which is the collision term. So, you have to somehow learn to deal with the complexities involving collision, and collision is actually in physics, this is a multi-body problem, that means many body problem involving the scattering between at least minimum of 2 particles, and it can also be extended to large number of particles. Even for a 2 particle system, if you want to express the collision term, this is written as what we call as the scattering integral. So, from a present state which is say k is your present state, is your wave vector, and it collides with another particle which is having k 1 is the wave vector of the other particle, and then after collision the respective wave vectors become k prime and k 1 prime. So, we want to therefore integrate this over the other wave vector values for k 1, k prime and k 1 prime, and therefore, we are calculating what is the net change in the wave vector due to scattering from its present state to another state, for example, from say k to k prime, and the other one is the inscattering, which is coming from the scattering from another state which is probably k prime, and if it scatters it, the wave vector comes back to the state k. So, the net change in this outscattering minus inscattering will be the scattering integral. So, which has to be integrated over the all other wave vector space except the current wave vector, which is k. So, therefore, this gives you the scattering integral and thus the collision rate of change of distribution due to collision. So, this is a very complex integral to evaluate, and again therefore, people maybe in physics have tried for some simple systems, but not very useful. Okay. Therefore, what people do is they apply what is called as the relaxation time approximation. So, it is a very simplistic, but a very practically useful approximation. So, what they say is that your entire scattering or collision term that we have on the right hand side can be simply expressed as a change from the equilibrium function. So, we can write this as f minus f equilibrium divided by some time scale tau. Okay. So, in fact, it should be I think the way we have written it, yeah, this is fine. So, this is your simplest way of dealing with the collision. Now, you will see that in this picture there is nothing talking about 2 particle interaction and how the wave vector changes after collision and all that. There is no information of any of that in this particular approximation. So, the inspiration for this comes from using what we call as the Bhatnagar-Gross-Krug approximation, Bhatnagar-Gross-Krug. So, this is simplified as BGK approximation. This is quite common in rarefied gas dynamics. So, in rarefied gas dynamics also the the Boltzmann transport equation is used, and there is also a similar problem with collision between the gas molecules, and there we bring in the BGK approximations very similar to the one that we have written here. So, we take an analogy from the gas molecule theory or gas kinetics, and then we apply that to also the other energy carriers and simplify the collision term. Okay. So, you should understand that this is a huge level of simplification, okay, starting from where we looked at into the complex collision integral and so on. So, we have drastically simplified the collision integral with something which is quite different. It does not describe anything about the change in the wave vector space and all that. But what this physically signifies is that if you put this back into the Boltzmann equation, okay. So, for example, we have written the Boltzmann equation here. If you substitute in place of the right hand side, okay, and you ignore all your advection terms, that is the rate of change of position, and in the case there is no external force, there is no change in the momentum also. Okay. So, in that case you have the time rate of change of the distribution function on the left hand side. On the right hand side you have the BGK approximation. So, in the case of negligible advection and force. So, therefore, we can find out the solution for this simplest case. There is no change in momentum space, there is no change in the physical coordinate, the distribution function only changes with time, right. This is the simplest possible solution that you can think of. What happens? What do you get here? You have df by f minus f equilibrium is equal to dt by tau. So, find out, integrate it, find the solution. I will come to the physical explanation of tau. So, through this we will be able to interpret what exactly tau is. Yeah, you can assume right now it is a constant. Okay. So, you can assume that your tau is a constant. This has the units of time, but it is different from the actual physical time here. So, we have f minus f equilibrium is equal to C e raised to t upon tau. So, this is the solution for this case where distribution function is not a function of space and momentum, but it is only function of time. So, from this you can get a feeling of what this tau or relaxation time, this is called the relaxation time now, right. What does this tau signify here? So, if you are looking at t by tau, which is quite large going to infinity, this should be e power minus. I think we have made c e power No, I think it should be F equilibrium minus, I think we have to make this as F equilibrium minus F, so that we know what we are talking about here. Just let me change this to F equilibrium minus F. So, we will have a minus sign here, and therefore, this will be F equilibrium minus F, and we have a minus sign. Okay. So, what this signifies is for large values of time going to infinity. So, what does it mean? This is going to 0. So, that means your non-equilibrium function is approaching the equilibrium distribution. Okay. So, you can imagine if you want to plot the equilibrium distribution, this is a kind of a uniform distribution in space. Okay. So, if you are suppose plotting this with respect to space or momentum space or physical coordinate space, this is maybe like a circle which is uniform, it is not changing with any direction. Now, if you look at the non-equilibrium function, that will be now distorted like something like this. So, this is your say F equilibrium and this is your F. Okay. So, you are all the time looking at the difference between these two distribution functions, and what it says is this relaxation time is some kind of a time scale over which you bring the non-equilibrium distribution function and you relax it to the equilibrium distribution function. So, this is a kind of a time scale, therefore, the relaxation time indicates some kind of a time scale about which this relaxation of non-equilibrium to equilibrium can take place. Okay. So, physical significance of the relaxation time is basically how long does it take for a disturbed system or the system which is actually having a non-equilibrium in a transport case to bring back the system to an equilibrium case. So, how does it bring back to an equilibrium? Only through scattering, only through collisions, right. So, this is how the collision is incorporated. So, the entire collision is incorporated only through the scattering time or the relaxation time. Otherwise, people may wonder what is this to do with collision, but the information about the collision is completely buried into this definition of the relaxation time. So, this tells you that through multiple collisions. So, the higher is the collision rate, the higher is the scattering rate, the faster is the return to the equilibrium. Okay. So, or in other words, if you are talking about smaller relaxation times, what does it mean? Higher will be the collision rate, that means the particles are probably packed quite close to each other. So, the relaxation times are smaller. So, quicker will be the return of the non-equilibrium to an equilibrium distribution function. So, this is the way that the Boltzmann transport equation with the relaxation time approximation is used. So, now the only unknown parameter that we have to find is basically what is this relaxation time, okay, and what does it incorporate and how do we calculate it. So, once you know that, we can attempt to solve the Boltzmann transport equation. So, this is the very useful practical approximation that is commonly used to solve the transport problems. So, if once you substitute this into the BTE, now therefore, you write let me check the signs. If I am saying it is F equilibrium minus F, it should be F equilibrium minus F, I think, right. So, yeah, it should be F equilibrium. So, I think here I should change the sign. Okay, please correct it. So, this should be F equilibrium minus F here. So, therefore, so this part again now changes to F minus F equilibrium. Okay. Some correction regarding the sign. So, this should be F equilibrium, so F minus F equilibrium. Okay. So, here also F equilibrium minus F. Right. So, therefore, this is your what we call as the Boltzmann transport equation in the relaxation time approximation. So, we write BTE under relaxation time approximation, or sometimes people call this as BGK approximation. And what is so important about this Boltzmann transport equation? Now, if you want to non-dimensionalize this, okay. So, let us consider a case without any external force. So, let us for the time being ignore the third term. You can choose some reference velocity u reference for the sake of non-dimensionalization, right, and therefore, you can substitute this reference velocity into the actual dimensional velocity. Similarly, you can choose a reference length scale. For example, if you are talking about something like heat transport between two plates. So, plate 1 maintained at a higher temperature Th, plate 2 maintained at lower temperature Tc. So, you are talking about the scale length scale, which is the separation distance between the two plates, which could be capital L. So, therefore, you can use the length scale to non-dimensionalize as L. This is your characteristic length scale. So, now substitute the reference velocity and characteristic length scale, try to get a non-dimensional form of the Boltzmann equation. So, for the time being we have neglected the third term, which is in the momentum space. We do not want to non-dimensionalize that now, okay, and see what happens. You do not have to non-dimensionalize the distribution function. Distribution function anyway, it is just a number density, okay. You do not have to non-dimensionalize, only non-dimensionalize the time, velocity and position. So, you can call something like V star is equal to V vector by U reference, and something like X star or R star, whatever you want to call, X by L, Y star as Y by L or whatever. Or you can say generally R star is equal to R vector by L. and you can call T star as T by some other scale. Now, in this case what will be the time scale? No, based on the reference velocity and characteristic length, L by U ref. So, you have df by final non-dimensional form dt star plus v star r star, let us say f. Okay. On the right hand side we have f equilibrium minus f by tau. So, what else will be there? So, we have a u ref by L. So, this should be L by u reference upon L. Okay. Right. So, therefore, now we can define. So, this is tau into u reference. So, how do you define this? This is what is the definition of, what is the relation between relaxation time and mean free path? This is your mean free path, right. So, therefore, this is your mean free path divided by L. So, what is this? This is your Knudsen number. So, therefore, the non-dimensional form of the BT will have on the right hand side the corresponding non-dimensional number, which is your Knudsen number. Okay. So, this is just like you are non-dimensionalizing your fluid mechanics or heat transfer equations. So, there you will have Reynolds number, Prandtl number. Similarly, here you have the characteristic non-dimensional number, which is your Knudsen number. So, therefore, what does it say? If you are talking about continuum, so that is the case where the Knudsen number, what is the limit for continuum? Going to 0. So, what does this tell about this equation? When the Knudsen number is going to 0, what happens to the equation now? Look at the terms. So, this term will now go to infinity. So, this will become the significant term, right. Therefore, the scattering will become the most important term for the limiting case where you are approaching continuum. That is because you have now too many energy carriers. So, they can collide. So, advection process will be very insignificant compared to your collision process. So, then that is your diffusion limit. So, all your macroscopic laws of continuum can be derived under this particular condition. Okay. So, for example, Fourier's equation, right, Newton's shear stress law, your Ohm's law, Fick's law of diffusion, all this can be derived under the limit where you are dominated by diffusion. Diffusion is nothing but collision of the energy carriers. So, this is possible only you are talking about very small Knudsen numbers where the scattering term becomes very significant and more dominant compared to the advection term. On the other hand, if you are talking about high Knudsen numbers going to infinity. So, this is your, what is this limit? Free molecular limit if you talk about gas dynamics. So, if you talk about nanoscale, generally this is called ballistic transport. That means, in this case what happens to this term? 0. So, there is no collision at all, right. So, Knudsen number is infinity, there is no collision between the energy carriers. That means, the transport is ballistic, it is like a missile. If you talk about a high temperature body and low temperature body here. So, the energy carrier from here directly goes, hits this particular boundary, right. Similarly, an energy carrier at this temperature will directly fly and hit this particular boundary. In between there are no energy carriers to collide and transfer the information. Okay. So, this is called a ballistic limit. So, they are just directly like a projectile shooting from one boundary to the other, and therefore, what happens, there will be a shock. So, when this energy carrier flies to the second boundary, it will encounter a different temperature, right. So, this has an equilibrium, for example, this has a certain distribution based on the temperature of this hot surface, and now it goes and encounters the second surface which is at a lower temperature, but it does not know that information because there are no energy carriers in between. So, there will be a shock. So, if you solve this particular problem using the Boltzmann transport equation, so what you expect is, suppose this is your TH and this is your TC, there will be a temperature jump like this and something like this, and again a temperature drop like this. So, the phonons, if you are looking at solid, the phonons cannot transfer basically all this information to the cold side, and similarly the cold side information is not transferred to the hot side. So, the phonons will have an energy density which is somewhere in between these two temperatures. At the boundaries there will be a discontinuity, because the phonon which is coming from the cold side will have a lower density compared to the boundary. Similarly, the phonon going to from the hot to the cold side will have a higher energy density compared to the cold boundary. So, therefore, it has to only now have a discontinuity as the solution. As and when your Knudsen number keeps smaller and smaller, you are approaching the continuum limit. So, you find finally for Knudsen number going to 0, what will be the solution? How will the solution look? This is your linear based on your Fourier's equation, the linear profile. This is your classical conduction profile, right. And why this conduction profile is linear? Because it is dominated by diffusion. Okay. So, when you do not have any information propagation by diffusion, it is completely only advection which transports, and therefore, you have this. So, this profile will be for Knudsen number of infinity, and this is your diffusion limit. So, now you understand that the Boltzmann transport equation is a self sufficient equation, it carries all the information regarding what kind of regime you are working at. So, you do not have to worry whether you have to solve separate equation at Knudsen number going to 0, because the same equation Boltzmann transport equation will be equivalent to the continuum equations at that limit, whereas it will also behave like a proper nanoscale transport equation at larger Knudsen numbers. So, therefore, this particular equation here is valid for all the Knudsen number ranges from 0 to infinity, right, because it can recover the continuum equations on the lower Knudsen number regime, and the higher Knudsen number regime it will become a unique solution. So, let us understand therefore little bit how to calculate these relaxation time, okay, and what does it basically involve, right. So, now when you are talking about scattering, so this is a very important topic, because the relaxation time is now, as I said, all the information about the collision and scattering between the energy carriers are buried into this particular parameter. So, therefore, what are all the different modes of scattering and how this information has to be conveyed to tau. So, one of the important modes of scattering is, if you take the case of electrons, it is electron electron scattering, for example. If you take the case of phonons, you talk about phonon phonon scattering, okay. Similarly, for gas molecules. So, now if you are looking at solids, for example semiconductors, where phonon transport is the most dominant. So, it is not only phonon phonon scattering, but you also have phonon scattering with other things such as impurities, okay. If you are doping the semiconductor, make it either a p type or n type. So, these are external impurities, and so these impurities or dislocations in the crystal will cause a resistance to the flow of these lattice vibrations. So, when you model these as particles, again you have to think about scattering of phonons with these dislocations or impurities. So, therefore, you can have a second type of scattering, which is your phonon impurity scattering, because the impurities themselves are not a physical carrier, okay. So, they are some kind of a resistance to the flow of phonons, and the phonons have to encounter them, and most likely they cannot pass through these impurities. So, they get scattered, and there is a certain scattering time associated with that. And finally, if you are talking about the high Knudsen number cases, what happens to the phonon which is travelling from the left to right? So, assume there is no impurity here, there are no other phonons. So, there is no phonon phonon scattering, there is no phonon impurity scattering. So, we can say that the right hand side term goes to 0, but you also have a phonon boundary scattering. The phonon just does not go and get stuck to the boundary, it also gets scattered from the boundary surface. So, it is a physical boundary, and the phonons cannot propagate through them. So, therefore, the third kind of scattering is a phonon boundary scattering. Similarly, for the electrons, you can also talk about all these, and you also have in most of the metals and semiconductors, electron phonon scattering, very important, because the electrons basically are free electrons which can move about in the crystal, and already you have these phonons. So, there are many instances where the electrons have to now collide with the phonons. So, in fact, this is the reason why you have electrical resistance in the first place. If there was no electron phonon collision, your resistance will be 0. The electrons can freely flow through the metals or semiconductors, but they are resisted by the phonon. So, therefore, you have a finite value of electrical resistance. So, in order to understand physically things like electrical resistance, thermal resistance, you have to look at the individual scattering. For example, electrical resistance can be explained by the electron phonon scattering, and similarly the thermal resistance can be explained by means of phonon phonon scattering. Okay. So, if you are looking at electron phonon scattering, this is a highly inelastic scattering process. So, you have two different energy carriers colliding. So, your energy will change post collision, your wave vector will change, okay. And also the collision between electron and phonon will not be just like that. So, the electrons cannot interact with all kinds of phonons. So, electrons will sometimes interact with the higher frequency phonons, most likely the optical phonons, and this will result in the release of some electromagnetic energy also. Okay. So, all these possibilities are existing. In fact, they use many of these principles, okay, to make semiconductor based light emission phenomena, and all this are related to such kind of electron phonon interaction. So, let us particularly focus on phonon phonon interaction, because if you are looking at heat transport in semiconductors. So, what happens is if you are talking about a system where you have two phonons, okay, let us say you have phonon 1 with wave vector k, the other phonon wave vector k1, and these two collide, and you have a third phonon which is formed. Okay, these two come and collide, and then these are virtual particles. So, you can say after collision it is equivalent to formation of another phonon with a wave vector which is k prime. Okay. So, similarly, if you are talking about let me use standard nomenclature K3. So, let me call this as K1, K2 and K3. Let me not use this prime again, because I have used this before. So, let me okay. So, similarly you can have similar collision between two phonons K1, K2, but there is a difference between these two. So, you can imagine this boundary, what I have drawn is the boundary of the Brillouin zone. Okay. So, this is the periodic repetition of this unit lattice structure, and when we talked about the phonon minimum wavelength, so we talked about say monatomic lattice where we have this kind of a structure, and what is the minimum allowable wavelength? So, therefore, if you are talking about this is your A, so therefore, this will be 2 times A. So, I have to redraw, I have not drawn this correctly, let me redraw this. So, this is your A here. So, therefore, the minimum allowable wavelength will be 2A. So, wavelength which is smaller than this does not make sense. So, you cannot have vibrations like this, which are much smaller than the lattice spacing. Okay. So, therefore, this lambda min is equal to 2A is going to define the boundary of the Brillouin zone, right. So, when we therefore define collision between two phonons, we have to make sure that the wave vector of the third phonon is not greater than the allowable wave vector space within the Brillouin zone. So, if this wave vector exceeds the Brillouin zone wave vector, so this will supposed to move out of the Brillouin zone, but which is not possible because you cannot have vibrations which are smaller than the lattice spacing. So, therefore, you have to correct this by pushing this back into the Brillouin zone. So, you have to therefore correct it by some reciprocal, what we call as a reciprocal vector, some correction is to be done. So, this is your reciprocal vector which makes sure that your solution is physical, and therefore, we correct it by that much and we push it back into the Brillouin zone. Okay. So, therefore, this kind of scattering where it does not exceed the Brillouin zone space, this is called normal scattering, and the one which has to be corrected back using the reciprocal vector is called the Umklapp scattering. Okay. So, if you want to write the conservation of momentum and energy for the phonon-phonon scattering, so in the case of, in the generic case for the conservation of momentum, so we have k1 plus k2 is equal to k3 for the normal scattering. However, for the Umklapp scattering, minus g. So, this reciprocal vector will be 0 for the case of normal scattering, okay, but is required for the case of Umklapp. But whereas, if you will talk about energy, that is perfectly conserved. Okay. So, these are the pre-collision values of wave vector and energy, and this is the post collision value, right. So, in other words, if you are representing by means of a plot of E versus k, for example, okay, the edge of the Brillouin zone is what, pi by a. So, therefore, if you are talking about the two phonons, so one which is having k1, the other which is k2. So, k1 plus k2, if it is greater than pi by a, okay. So, this is corrected by the reciprocal lattice vector and brought inside, because this is your maximum allowable value of k corresponding to the minimum wavelength lambda. This marks the edge of the Brillouin zone, right. So, in fact, if you take therefore the normal scattering, the momentum is perfectly conserved and there is no problem. Now, in the Umklapp scattering, this is where the reciprocal lattice vector is used, because now this poses a resistance now to the momentum. Other words, I mean, in the normal scattering case, there is no resistance to the collision of the phonons and transfer of momentum, whereas in the case of Umklapp scattering there is a resistance to the momentum transferred. So, the momentum is brought down by means of this reciprocal lattice vector, reciprocal vector. So, therefore, this is the one which results in the thermal resistance. Okay. So, on a fundamental basis, so if you want to describe why we have a finite thermal conductivity of a solid, so that is because of the presence of Umklapp scattering. If there was no Umklapp scattering, your thermal conductivity would have been infinite, because the phonons can flow easily without any resistance. They can transfer the momentum, they can transfer the energy. So, conservation of momentum is satisfied. So, the momentum will not come down, right. So, but what is resulting in the reduction of the momentum is the Umklapp scattering, which brings down the momentum and therefore builds a resistance for the flow of heat. Okay. So, this is the most important scattering mechanism when you want, when you are considering the effect of finite thermal conductivity. Okay. So, therefore, to summarize, so Umklapp scattering process contributes to a finite thermal conductivity. So, if there was no Umklapp scattering, so you will be having infinite thermal conductivity. And whereas your normal scattering does not contribute to any resistance, no resistance. So, through this you therefore, you can explain through the electron phonon collision, you can explain the finite electric resistance, and through phonon phonon Umklapp scattering mode you can explain the finite thermal conductance. Okay. So, now how do we therefore calculate all these scattering modes? We have normal scattering, we have Umklapp scattering, we have phonon impurity scattering, phonon boundary scattering. So, how do we calculate all of this? So, there are some standard expressions which I would just like to give. For example, if you take the case of Umklapp scattering, so the relaxation time has a particular empirical correlation which is like this. Okay. So, now these are constants, capital B and small b are constants, and your theta d, you remember what it is? Your d by temperature, and T is your actual temperature, your physical temperature, and omega is the frequency. So, all this in Kelvin. So, depending on the kind of material, these constants can take different values. Okay. So, this is how empirically the phonon scattering time is calculated. Similarly, if you are looking at phonon impurity scattering, so the expression used is subscript is I, A omega power 4. where A is also another constant. This phonon impurity scattering can be imagined like Rayleigh scattering. In Rayleigh scattering also we have fourth power dependence to frequency, the scattering time, okay, that is the Raman scattering or whatever we attribute. The sky color is blue because if you look at the frequency, the higher the frequency, the greater the probability of scattering. So, that is why we have this. So, this is similar to your Rayleigh scattering modes. So, that is why we have fourth power dependence on frequency. So, therefore, we have all these different scattering relaxation times. So, therefore, how do we calculate your total relaxation time? So, we use what is called as a harmonic mean, or this is also called as Matthiesian's rule, Matthiesian rule, which is just a harmonic average of. So, therefore, 1 over tau will be 1 over tau u, this is your Umklapp scattering time, and the other is your phonon impurity scattering time. Okay. So, using the Matthiesian rule, which is the harmonic mean of the different relaxation times, you can get your final relaxation time and substitute into the Bt. Okay. So, we will stop here. Okay.